So we have a basic nav mesh setup, and we can generate entities to run on this nav mesh. I also have set up basic physics so we can have a nav mesh agent run at the same time that we're using dots physics. So we're using a managed nav mesh agent along with dots physics and dots entities. This is all very loosely held together, but that's something which I'll worry about later. Since I now have these two elements set up, I have the basis for working on the AI for the character. And the first part of working on the AI for the character will be working on perception for the character. Traditionally, when we talk about perception, we'll have the 5 senses. However, for game characters, the majority of these senses will not matter. For example, if we touch an enemy or NPC, that will be a direct system which will be created via a trigger. It will also be part of the damage system. So this is something which does matter. However, this will be an element of more complex gameplay systems. It is not a base interaction that we need to deal with. It is also a system which will be triggered not by the NPC, but from the player. So essentially, an NPC doesn't have touch until the player touches them. The next two are taste and smell, and both of these are things which you can bring up in games as conversations and are generally interaction driven. Of these, smell has a more general interaction. However, this doesn't necessarily have to be driven by anything which interacts within the scene, as most of the effects for smell will be audio cues. They could also be animation cues, but we can drive these through general global parameters rather than any parameters which have to reside on the NPC themselves. Both of these are also driven by the nature of the game which you're creating. For example, taste will often be associated with things like hunger systems, and will usually be an audio or text reaction. Hunger systems are usually controversial, and people generally tend to not like hunger systems. Hunger systems are also a mechanic which is very far removed from the reality, as starvation is a slow, long-term process. So unless they're a central mechanic to the game, they're something which can generally be avoided. The next sense is far more complex. This is a sense which we can give to the NPC, and this will be a sense of hearing. Although there's an argument as to whether we should actually give the NPCs a sense of hearing or not, as this is something which also does not need to be specifically part of the NPC logic. Here this should be very dependent on the type of game we're making, but whether the hearing functionality should be driven by the NPC is actually a very big question. So for a basic example, if we have this as our NPC, and this is our character, when the character moves, this character will make a sound, and this will be distributed in a radius around the character. If the NPC is out of this radius, the NPC will not hear it. And if the NPC is within this radius, we will raise the chance of having the NPC hear it. There are two main options for approaching this, and the first would be to have the NPC have its own hearing radius. The problem for this is that this radius will have to be tested for every single NPC in the game. And since this is a physics object, we'll be interacting with triggers for every single NPC all the time. Which means we need to decide, are the NPCs going to be interacting with each other based off hearing? However, another option which could be far more performant is to track the noise the player makes within this radius, and to specify this radius as the player's noise radius. The character's movement will then define whether the character is loud or not. And if an NPC is within this trigger volume and the character's movement is too loud, we will then send a message to the NPC telling it that it has heard us. This will give us one trigger volume rather than multiple, so it will mean that we have far less possible interactions within the scene, which could make our physics slightly more efficient. This system can also work for objects. For example, if we are throwing a grenade, when the grenade lands or explodes, we can generate a sphere that will represent the sound for this grenade. This trigger volume will trigger anything within it, and then it will be despawned. This means that the sound emitters can be spawned dynamically, and will not have to be tested every frame for every single character. Sound, however, is a gameplay mechanic which we do not necessarily always need, so this will not be called to the characters. So I can worry about this if that kind of gameplay ever becomes part of my controller, which means that we only have one sense left, and this sense will be intrinsic to every single character within the game. And the sense which we need to give for all our characters will be the sense of sight. For a vision system, we need to consider what types of vision there are. Essentially, we have a vision range which is larger than 180 degrees. On both sides of the head, the angle of the eye and the curvature of the cornea will give us a viewing angle which goes 20 degrees beyond being perpendicular to the head. So the viewing angle is actually slightly greater than 180 degrees, and we're actually very susceptible to movements within this range of our vision. We'll then have two major peripheral vision ranges. The first of these will be about 60 degrees, which is part of the peripheral vision which actually extends behind us. So there's about 40 degrees in front of the perpendicular and 20 degrees behind it. and then another 30 degrees. The main cone of vision will be about 18 degrees. There are small cones of vision within this, but we do not actually need any more detail than this. There also is a slight overlap between our peripheral vision and our main field of vision, which will be defined by the macular section of our retina. For the moment, we are only going to focus on the main cone of vision, and we're going to ignore peripheral vision. So there'll be a number of things which we'll need to decide on for this vision code. Most of these are practical concerns which will come later. However, we should take them into consideration as they may become relevant in the future. The distance which we can see is far further than any NPC would ever require. So what we really need to take into account would be a relevant field of vision in which the NPC would be able to identify things. You'll generally be able to recognize a person clearly at a distance of about 100 to 200 meters. This is the distance at which an NPC should be able to notice another entity. However, there should very rarely be an interaction at this distance, other than the NPC looking at the character. So this is the position in which you would consider having a look at control. However, the cost of actual head animation at this distance may be too great, so this is something which we would have to test. So 200 meters will probably actually be a little bit too far, but we could consider interactions at a range of about 100 meters. To justify an actual reaction, we would want a distance of about 10 to 20 meters, as this would be the most comfortable distance for basic reaction. The next thing to do is decide how we're going to have a collision volume. We could drive this with a cone, although to be physically accurate we would need to drive this with an ellipse. We can also drive this with a frustum, or we can drive this with a square box. I'll initially be driving this with either a box or a frustum, and I will probably settle on the box for the final setup, as there's very little physical difference between having a box, a frustum, or a cone, especially when you're talking at a distance of less than 10 meters. So to calculate this, I'd want to base the frustum off the far point of the frustum, and the ratio for this frustum will be about 1.777777 for the length to 1 in the height. This ratio may seem slightly familiar, and it is actually a very commonly used ratio, and that's because we can approximate this ratio very easily with the value of 16/9. And this is the ratio which was chosen for HD TV. There's a little bit of a story behind this ratio, so I'll go into a bit of a tangent here explaining the history of it. Whether this was the best ratio or not is questionable. There are of course other options, and these are better for composition. For example, we could have the ratio to 1 to the square root of 3, or we could have the ratio of 1 to the square root of 5, both of which are objectively better for composition. A lot of the reason why this ratio was decided on comes from the history of cinema. Originally, cinema had a ratio of 4/3. All of your original films were recorded with this ratio, and when the television was invented, it used this ratio because this ratio matched up with film. Hollywood reacted to this by developing widescreens, and this was made possible through the development of the anamorphic lens. So when the spec for HD was initially being developed, they initially wanted to match widescreen formats. There are a number of theatre aspect ratios, but the most common is about 1.85:1. However, Hollywood refused to let HD use exactly the same ratio as film, so a different ratio was chosen, and the ratio that was chosen was based off the approximation of human vision. Essentially, this is the size at which a human can focus on and have everything in focus clearly. So the TV is attempting to give you the maximum possible clear vision before you pass into peripheral vision, so that you have the entire picture in focus. This kind of rule doesn't apply for everybody, but it is valid for about 98% of people if I remember correctly. So essentially when we're looking at the screen, we'll have everything in focus, and anything on the edges of the screen will be blurred. Then more anecdotally, there were two formats chosen for this, and these were a broadcast format and a media format. These were essentially the 1080p format and the 720p format. You often hear people talking about this as being related to Xbox versus PlayStation, but contrary to what people say, the game industry had very little influence in this. 720p, which is actually the biggest achievement within the HD spec, was actually designed for broadcast television, and at the point HD was released, the main form of television broadcast throughout the world was radio transmitter broadcast. Satellite broadcast was becoming more common at this time, but it was not yet the main form of transmission, and in this case, 720p was actually slightly beyond what was thought possible in terms of radio broadcast. You need to be able to reflect information off the ionosphere, and 720p actually required more information than was thought possible. So 720p is actually a technical milestone in terms of radio broadcast and not just in resolution. But that's actually why there were two formats for HD TV. The one was for radio broadcast, and the other was for physical media and cable. The HD DVD and Blu-ray battle actually had nothing to do with the spec. and the spec was in development long before either of these formats was developed. However, most of that is irrelevant. The most important thing to take out of this is a 16:9 ratio cube will give us a reasonably accurate trigger object for our vision measurement. I'll begin this as a vision box and may well end as a vision box, as that should be more than accurate enough for most cases. So essentially I'd have a distance of about 20 meters for my main interactions. Near the character will have the initial frustum, and this will have the ratio of 1.7777/1. Then for the actual player, we will want to calculate the frustum at about 20 meters, and calculate the factor which we'll need to multiply this for a reasonably accurate view. So I'll now start working on this in Unity. If we look at our scene, we currently have a NavMesh agent that is moving along the NavMesh. We also have a test physics object which will fall and collide with the ground. I'll be making a couple of adjustments to the scene before we begin. I'll begin by duplicating our test cube. I'll make 3 copies of the cube. These, however, will not be used to test the physics. Instead, we're going to use these to test our character. So I'll name these Trigger, Trigger 2, and Trigger 3. I'm going to select all of these, and I'm going to change the way the physics is set up for them. These are going to be trigger objects, so they will not actually move any other physics objects, but we will be able to tell whether they touch other objects. In the solver itself, I'll turn on is kinematic. This means that we will move these objects, and they will not inherit any movement from the simulation. After this, I'm going to update my NavMesh agent entity. I'll add a child object to this. This child object will be a cube and will represent our vision. I'll raise this up slightly so it's closer to where the character's head would be, although at the moment this will not really matter and this will be a very rough estimate. I'll edit the box collider and I'll extend it out a little bit. We'll specify that this collider is a trigger as we don't want this interacting with the environment, and this will give me the basic setup for the character's physics. So now I'll start working on the logic for the character, and there's some problems which we'll need to deal with before we can even look at the triggers. When we play the scene, we'll see that the entity is not actually moving along with the NavMesh agent, and this is to be expected. I've got the NavMesh working, but I haven't worked on the entity at all. This is the same as the player movement, where we need to update the movement of the entity based off the movement of the game objects that we're attaching it to. So to do this, I'm going to need to update the scripts for my NavMesh agent, and I will begin by updating the authoring script for this entity. I'll begin by making a couple of components, and the first of these will be a tag component. This will be a public struct, and I'll give it the name tag NPC. Essentially, this will define what an NPC is. This will inherit from iComponent data, and this will be an empty struct. In the Baker script, I can add this component to my entity. I'll use the add component method. The first argument will be my entity, and the second argument will set my tag with new tag NPC. This will give us our tag, and we can now use this within our system. So I'll now work on the NavMesh agent system. Here I'm going to update the for loop where we are evaluating our NavMesh agent. Currently we have a reference for our NavMesh agent. We also have a reference for our target value, which is setting the NavMesh agent's destination. We'll add a third value here, which will be the transform, and this is going to be the transform of our current entity. This will be a component that I want to modify this, so I'll actually want a reference for the component. Because this is modifiable, this will be ref_rw. The type here will be local transform. I then want to specify that this is only going to happen with the NPCs, so I can call the with_all method, and the component that we're going to require will be the tag NPC component. We can now update the transform for our entity. This will be transform.value_read_write. I'll then update the position with .position. I'll get the position from my NavMesh agent with agent.navmeshAgent. I'll then need the transform, which I'll get with .transform, and we'll get the position with .position. I'll then update the rotation, and this will be done with transform.value_read_write.rotation. This should update our character, and we can now test this. So I'll return to Unity. Our character is moving, and the cube is now following with the character. We do, however, have no visualization for the physics component. I will not get a good display for this within the viewport, so to debug this properly, we'll use our global physics display. I'll draw the collisions, and we'll see that my physics object is moving with the character, although the direction that it is facing in is not particularly good. I will update the physics object as this is not correct. This should be facing down the Z-axis. I'll give this a distance of about 5 meters, and I'll offset the center and Z by half of this distance, so this offset will be 2.5 meters. When I run this again, my vision is now facing in the right direction. I'm now going to create a couple of scripts to evaluate my physics object. I'll place these along with the scripts for the NavMesh agent, as these essentially form part of my NPC logic. The first script that I add will be a Baker script. I'll give this an authoring prefix. This will be for my NPC, and this is going to control the vision of the character. I could name this after the physics, but vision is more appropriate to what we're actually doing with it. We'll need a second script for this, which will be the corresponding system, and this will be called System NPC Vision. These scripts will be used to calculate our collisions. I will add the script to my vision cube, but this will not be the first thing we test. Instead, that will be the trigger cubes, so I'll need to add the script to all of the trigger cubes as well. I can now start editing these scripts, and the first script that I will edit will be the authoring script. I'll need to add some components for the physics object, and the first of these will be a tag. This will be a public struct. This will have the name tag NPC vision, and this will inherit from iComponent data. This will be an empty struct. Next, I'm going to create a Boolean component, and this will be called hasTarget. This will have a single member, which will be a public bool, and this bool will be called value. I can now add these components to the entity within the Baker. First, I'll need my reference to the entity, and this will be called entity. I'll use the getEntity method, and I'll set the transform usage flags to be dynamic, although we are unlikely to use the transform on this at the moment. I'll add the components using the addComponent method. The first argument will be the entity. I can then add the tag NPC vision component to this. I can then duplicate the addComponent function, and here the second argument will be specifying my hasTarget component. By default, I'll give hasTarget a value of false. That will attach my components to the entity, and I can now use these within the system. For the physics trigger, we're not going to be running a loop within the entity. Instead, we're going to be creating a job. This kind of physics interaction is rather arbitrary. It is not the kind of thing which ECS deals with well. The operations which perform best with ECS are operations which you loop over, and this works best for actions which are going to happen every single frame. So this will break from the ideal ECS behavior, and will take a slightly different approach to ECS. We'll work within the onUpdate method, and here I'm going to get a reference to my simulation. The simulation is a global value which is referenced in the type simulation singleton. I'll store this in the variable simulation. I'll get this with systemapi.getSingleton, and we'll look for simulation singleton. I'll then need to give this entity a dependency, and I'll do this with state.dependency. This dependency is going to be a job. I'll add this as a public struct. This will have the name vision trigger. This struct should be burst compiled. This will inherit from iTriggerEventJob. I'll need to implement the interface within the struct, which will give us an execute method. Next, we'll need to get information from our entities, and we need to do this in a rather arbitrary manner. First, we'll need to look for entities with a hasTarget component. So we want to construct an array of these, and for this we'll use a component lookup. This will be a component lookup of the type hasTarget. I'll store this in the variable target lookup. I can now add this to my dependency, so our dependency will be set with a new vision trigger. I'll need to populate the variables, and the first one will be the target lookup. I'll change this name to hasTarget lookup, as that will be more accurate. This can now be set with systemapi.getComponentLookup, and this will be of type hasTarget. This should initialize the vision trigger struct. This is a job though, so we will need to schedule it. The first argument here will need to be a reference to my simulation singleton. This is specified within my simulation variable. The second argument will be my job handle, which will be state.dependency. All of the vision entities should now run a job which will test for trigger events. However, all this will currently do is throw an exception. That's not how I want to test this, so I'm going to update the logic with something more palatable. Here I'll have a conditional which will be if hasTargetLookup.hasComponent, and we're going to test this against the entities which are triggered by this event. I'll specify this with triggerEvent.entityB. This gives me something to test, and I now can print out a value based off this test. I'll do this with debug.log. I'll specify a string which will say collision, and I can pass a value into the string. And in this case, I'm going to print out the entity that we're colliding with, which we'll specify with triggerEvent.entityB. This should give us enough to test if the trigger is working, so I'll return to Unity. I'll turn off the visualizations. I can then run the game. I'm going to select one of my trigger boxes, and I'm going to move this. I have the two boxes directly next to each other, so this should be reasonably easy to see. And when they overlap, I should get a printout that prints out the name of one of these entities. And this means that we are getting our collision to work. We now want these triggers to work with our NPC. And when they collide, we want the NPC to register that this is a new target to look at. And the NPC will then chase after this trigger object. I will also want to eventually set this up so that I can track whether I've collided with the target or not. And this is what I'll eventually use the hasTarget variable for. This, however, is not yet something which I do need to use, and I'll focus on the targeting system first. So what we'll work on next is we're going to take a cube for the vision. This cube will need to edit the values on its parent entity, and doing this will cause this entity to update the target value. And updating the target value will automatically update what the NavMesh agent is doing. To do this, I will need to update my NavMesh agent again, and I'm going to need to add a new component to the NavMesh. Essentially, we need to add a reference to an entity to the script. I'll be working on the authoring script for my NavMesh agent, and here I'm going to add a third component. This will be a public struct, and I'll call this NPC other. This is not specifically an enemy, and we're already defining target as a position, so another entity that can be affected by this entity will be referred to as other. This will inherit from iComponent data, and it will have one member variable. This will be a public entity, and it will be called other. I can add this component to my NavMesh agent with add component. The first argument will be entity, and the second will be a new instance of NPC other. We should now be able to update our system to use these components. The first thing that we'll need to do within the script is find the parent of our trigger item, specifically the vision trigger item. I'll be extending what I'm storing within the script, as you'll no longer just be looking for the hasTarget component, and instead we'll have two component lookups. The first of these will be looking for a parent object. The parent object is actually part of a transform, and it should be recognized as a default component. I'll store this in the variable parent lookup. The next component that we'll need to edit will be our NPC other, and this will be stored in the variable other lookat. These two components will now need to be set when we create our instance of the struct. So after we've set our hasTarget lookup, we'll set our parent lookup. I'll set this with systemapi.getComponentLookup. The type will be parent. This will be followed by the other lookup. This will also be set with systemapi.getComponentLookup. The type here will be NPC other. Our parent component is not being registered, and this is because we need to include the Unity Transforms library. This will be done at the start of the script. This will be done with using unity.transforms. So now I can use this to find out if my trigger has a parent item, and our logic will be based around the parent lookup. With any collision, there will be two entities, and we need to know which entity is which. So I'm going to create two variables to store our entities. Both of these will be of type entity. The first one will be ego. This will be the current entity. And the second entity will be other. And this will be the entity that we want to use for our target. I'll then want to test my parent values. I will do this in a conditional. If parent lookup .has component, here I'll be looking for the trigger event.entity A. So if entity A has a parent, the ego will be entity A, and I'll set this with trigger event.entity A. The other will be entity B, and this will be set with trigger event.entity B. We will need to test for the opposite case, so I'll duplicate this expression. Here I'll test if the parent lookup is equal to entity B. In this case, the ego will be set by entity B, and the other will be set by entity A. So essentially, if our vision cone has a parent, we should be able to select that parent. There are a lot of flaws and loopholes here that I will need to plug, but I am looking for the initial testing and the basic logic first. I can now set my other value on my NPC, and I'm going to be doing this using my component lookup. In this case, the other lookup. The index here will be set with an entity number, but I'll leave that till later. This will be set with a new NPC other component. I'll initialize this by setting the value, and the value will be set with our other entity. I'll then need to specify which entity I'm going to be looking for with the other lookup, and that should be the parent of our trigger object, and we'll get this with our parent lookup, and the entity that we're going to look for the parent on will be our ego. This, however, will not give us the actual entity. We need to specify this specifically, and I'll specify this with .value. I am setting the wrong value for the NPC other. The entity name here is actually other. This should now give our entity an other object, and we should be able to use this to set our target position. I can now test this within Unity. I can select my NavMesh agent NPC entity, and this should now have an other component. Currently, as we do not have anything set here, this has a value of none. I'll pin this entity in my interface and I'll select one of my target cubes, and I want this to collide with the vision box. So I want to move this in front of my NavMesh agent entity. When this collides with the trigger, we should see that the other entity updates, and that this is now set to trigger 2. All of my trigger objects should allow me to change this, so I'll select one of the other trigger boxes and I'll try and trigger the character with it. When I do, the value now changes to trigger. I'll try to set this again with the trigger box 2, and the trigger is still working correctly. So we can now trigger our entity so that it will recognize another entity based off its vision box. And now we want to update our logic based off this. I can now work on the system for the NavMesh agent, and here I want to make this update my target information. To do this, I'm going to add a new for each loop at the start of the script. There will be 2 components which we try to work with here. The first will be the NPC other, which I store in the variable other, and the second will be the NPC target, which I'll store in the variable target. I'll look for these using system API.query. In the query, we'll specify that we're looking for an NPC other as well as an NPC target. I will specify that we're only going to look for an NPC here, and we'll do this with the withAll method. The type that we'll specify here will be tag NPC. We're now going to perform operations using our other entity, but first we want to make sure that this actually exists. Here we'll have a conditional, and this will be if other.other is equal to entity.null, which will essentially test if we have no entity. If we do not have anything, we'll continue without updating our loop. One thing that we should note here is we have to use entity.null. If we just try and do this by specifying null, this will not work correctly. I then want to get my value from the entity using a world position. So I'll create a local to world matrix and I'll call this transform. This will be set with system API.getComponent. Here I'll look for a local to world component. This transform will be on our other entity, and we'll get this with other.other. We can now use this to set our target, but to set our target we need to make sure we're setting a reference to the target. So I'll need a reference read-write for our NPC target. We should now be able to update our target using target.valueReadWrite.position, and this will be set with transform.position. This means that our target will no longer be updated by items which we set within the viewport. Instead, it's going to be updated by other entities which exist within our scene. I can now save this and we can test to see if this will work. I'll press play and my entity will move to its default target. In the inspector, we should see that this does not currently have an other specified. So I can get one of my trigger objects and I can attempt to trigger my entity. I've triggered the NPC, and now the NPC should attempt to follow the trigger object. I should now be able to select one of my other trigger targets, and we should be able to get the NPC to swap to this target if we intercept it. I'm successful, and now the NPC is following the second trigger target. We should then be able to make it follow a different target. This is of course if I can get the trigger aligned correctly, and this is not something which I managed to do. And here I try to get him to follow, but there's actually another trigger in the way, and that trigger interrupts him. This means that I now have an NPC targeting system, and I can trigger my NPC to follow other items within the scene. We do have some errors showing up, and these are actually not related directly to our system, instead they're related to general physics issues. If my trigger object collides with a non-physics trigger object, we do get an error. This is something which we will need to test for and create guards against, as this is not really a desired situation. We do, however, have the basic logic that we want, and it is working correctly, and we can worry about tweaks to the AI later.